Hello, welcome to Lab 6, Magnetic Braking. The purpose of this lab is to study the magnetic induction that happens when a bar magnet falls through an aluminum tube. We'll be comparing this to a computational model, in the system being the bar magnet and the aluminum tube. The results were that experimentally 0.2 seconds and computationally 0.8 seconds. So the fundamental principles we'll need to know for this are Faraday's law and the Biot-Savart law for current. So Faraday's law says that the number of loops times the negative of the change in magnetic flux over time is equal to the non-Coulomb EMF around that loop. And then Biot-Savart's law says that delta B is equal to mu naught over 4 pi constant times current times a little part of length crossed with r hat over r cubed. We're going to combine these to determine the forces at play. And then we also just need Newton's law because it's something in motion. So the experimental procedure you'll see here is you drop the magnet multiple times and measure how long it takes to fall out. And one thing you can notice is it takes longer than you would expect without the tube. So the assumptions we make here are that there's no air resistance, the bar magnet acts as a magnetic dipole, and the only forces are magnetic and gravitational. So here's the data. The tube dimensions are recorded, as well as the bar magnet properties, and here you can see 5 trials, average drop time of 1.25. So here is the computational model. This is a visualization of the fields as it drops down. So because there's 2 poles, the induction happens differently on each, but both actually end up pushing it up. And as you can see here in the graph, it starts off falling, and then because the flux is increasing, it's then going to, in the middle, act equally to the gravitational force. And that's why the velocity is constant with Newton's laws. And then eventually it runs out of the tube, so there's less like inducting material near it. So that's why then the velocity changes again. So errors and assumptions, we used our like phones to time it, so that's not that accurate. There could also be some friction if the bar magnet bounces around as it goes down, wouldn't take a straight path necessarily, and there is air resistance in the lab. So what if the tube resistivity of the material was close to 0? So in this case, the induced voltage of the falling magnet would be the same because nothing's changed there. So the current going around the loop would be the same, and then R is lower, so I is higher, meaning a higher magnetic force acting on the magnet. And then what if slots were cut into the tube? Throughout the whole tube, this would mean that there is less current loops going around, and this basically would weaken the magnetic force that the induced current creates, meaning the magnet would fall faster. Thank you for watching. I think this is our last lab ever, so it's been real.